Hello, I'm Dr. Harper. Welcome to Week 2 in Forecasting for Operations Management BANA 3000 Section E01, Spring 2021. This week, we'll look at forecasting and we'll get more into Excel. And forecasting is the excellent place to start because you have to know what your demand is before you can start your operations. So let's bring up the notes. Okay, I have a summary here. I start, and this is going to be Chapter 4. Beginning on page 133 in the textbook. I will not cover everything in this chapter, but I'll cover just most of it. And I'll cover what I feel is a good foundation, a good basis to build. So first, this is a summary. First, I have an introduction on page 136, and those first few pages is a good introduction to easy read. I won't ask you anything about that specifically. I'll focus on the actual creating a forecast. I will introduce some terminology here that's going to be a little bit that the textbook does not do. They kind of talk around it, but I'll specifically identify these six terms: stationarity, non-stationarity, random and trend, cyclical, seasonal components. Okay, now they have a 7-step procedure. I will replace that with a 4-step procedure or 5-step procedure, and I'll just allude to that as we work through the problems. And then we have qualitative methods. I won't really cover those too much in this course. I will focus on the quantitative methods, and there they are. These are the 5 on page 139, beginning on page 139, and there's where they list them. So I will cover the quantitative methods, and these are the pages that I will cover with the examples. Then I'll cover on page 145 and 46 and 47 measuring errors, MAD and mean squared error, and then seasonality and seasonal variation in data. Now, this right here, as far as I'm concerned, comprises a very good foundation for people to start forecasting. Probably 75, 80, in some cases, 90% of common forecasting problems that will cross your desk when you start an industry. So let's start. Okay, first in the introduction, here is the forecasting. There's 2 types of forecasting: time series forecasting and causal. Time series, essentially, the time series is a variable as a function of time, and you think of demand varying over time. It increases, decreases, increases, decreases, and the demand can be measured by in Starbucks how many people are coming through the door. During rush hour, there's going to be a lot, and then off hours, it's going to go down. So that's your demand over time. Now, demand time series is a variable demand over time. So your time series forecasting is using past time series to forecast the future. In other words, in the past, at 8 o'clock, Starbucks has a lot of people. At 10 o'clock, they go down. So we use that pattern every single day to forecast the future. Now, time series forecasting uses patterns in the past to forecast the same patterns in the future time series. For example, if an increasing trend exists, then continue the trend to forecast the future. Models include, but not limited to, moving average, exponential smoothing. We'll start with those. Okay, next, and there'll be others. All the others I mentioned. Causal forecasting. This is using variables different from the time series to forecast the time series. For example, leading indicators. Using increased numbers of sales calls is a leading indicator of sales. Or instead of calls, I could say sales reps. Sales reps. So if we have more salesmen or saleswomen, and we have a broader sales force, that's a leading indicator of having more sales. And so we hire twice as many salespeople. And then what's going to happen is, leading indicator down the line, we'll have more sales. So that's an example. Now, models include, but not limited to, regression. Okay, now the terminology of stationarity and non-stationarity. Components, random, trend, and cyclical. These are important. The textbook doesn't go into them in as much detail as I think you should know when you start working, because these terms are fairly common. Okay, stationarity, the overall nature of a time series. I have 2 time series here. Now this time series here, now notice this is over time, and basically the overall nature of that time series is constant is stationary. Now this time series starts increasing, it keeps increasing, and keeps increasing. So the overall nature of that is non-stationary. It keeps going up. Okay? Now components. Components definition or description is a cause of variability within a time series. So stationary talks about the time series, the overall nature. Components talks about the cause of variability within a time series. Well, first of all, you have a random component. And here I take this time series here, and I see there is variability. Now, what I mean by variability, if I can come up here and draw a straight line, if I straight line through the data, like this line, this line right here, there we go. And let me just make that fatter, larger, bigger. That's good. That's a little too good. Let me bring it back down. Let's see. There we go. That's good. Notice there's variability around that line. So this line could be called the stationary mean, but the variability around that is due to unexplained variability, because there is no pattern. There's no pattern we can capture. It's just up and down, up and down, up and down. It's volatility. Okay, it's noise. So volatility noise is really called a random component. So the cause of that variability around the mean, or the stationary mean, or the flat line, or the overall nature, the variability within their overall nature, is unexplained because there's no real pattern we can capture. So that's called a random component. Okay, now we bring down here to the trend component. Now we can see there is variability around this line. At the beginning of the time series, it's below. At the end, it's above, because this is a non-stationary time series. Well, the variability around the stationary mean due to the non-stationary nature of the time series is called a trend component. So now we have a trend component. There are different types of trends. We will look at just linear trends. Next is cyclical. Now for a cyclical component, cyclical just means a repeating pattern. It could, if we have an annual time series, which is you aggregate data over a year, and you have 10 years worth of data, and it goes up and down, up, that's cyclical. So a cyclical simply means a repeatable pattern. But if you have a repeatable pattern that repeats every year, an annual repeating pattern, that cyclical pattern is called a seasonal pattern. It's called a seasonal component. So a cyclical component just says it's repeating. It's repeatable, and we can capture that and forecast the future. But a seasonal component is a cyclical component, a special kind that repeats every year. So every year it repeats that same pattern. And so this is what we'll be looking at in here. Okay. Next, the 7-step process that I bring down to, I'll have 4 here. Above I had 5. And so 5 would be lessons learned. Well, what do I mean by lessons learned? You plot the time series to determine stationarity. You take the plot and assume your components. You say I have a trend component, I have a seasonal component, something. Select your model accordingly. Make your forecast. This is what we'll be doing in this lecture. Now I put lessons learned as the 5th step in this problem-solving approach. What I mean by lessons learned is back up and say, okay, well, how accurate is it? How good is it? Did we do it the right way? Should we do it the same way next time? Can we learn from this? Can we have lessons learned for future forecasts from the past? Are we learning how to do this better this time? And so don't just blindly believe the numbers. The numbers are just representation of reality. So the lessons learned, you back up and try to learn from how well did that perform in the past? How well do we think it will perform in the future? How much value should we give to these? So the lessons learned are going to be important. Okay, so now then we go into the quantitative methods, which I'm getting ready to do. And we'll do measuring forecast error. And this answers the question from the lessons learned, how good are our forecasts? And then into seasonality. So here's the quantitative forecasting agenda. Okay, here we go. Let's get into the details. Each approach, down here, each of these approaches will be illustrated using Excel. So I'll be bringing in Excel, and I posted Excel in Canvas, and everything in Chapter 4 will not be covered. I only covered parts of it that I think are important. Now, there are things in the chapter in the textbook that he covers, and it's a really good extension. But if you understand these 7 different approaches, then it's easy to extend it to the others. Okay, so I'm laying a foundation. Okay, really quick, notice I give the approach and the page number, and the example. EX is example. Example 1, example 3, example 4 and 5, example 8. Down here, example 9, 10, and 11. And then at the end, I deviate from the examples in the textbook, and I say, putting it all together, I'm creating data and say, okay, putting all this together, here's the takeaway. Here's how you would approach a real problem in industry. So let's go through these real quick. Okay, first of all, the naive approach, page 140. The naive approach is a special case of a moving average approach. So both will be covered next here. So I'm covering moving average. Well, moving average, naive is a special case of moving average. So looking at page 142, example 1, moving average, this really illustrates noise dampening. I'll explain what that means. A moving average determines a forecast using the average within a window or an interval. Now, a moving average is applied to a stationary time series with a random component. So we're looking at that first stationary time series. Consider 2 examples. A moving average and this example are, these 2 examples will be an example 1. Will be the naive up here and the moving average. The 3 here is the window or the interval. Okay, a moving average with a window or interval of 1 will report a forecast as the last value in the time series. A moving average with a window of 1 is represented as MA1, where MA is moving average, and 1 is a window or interval of 1. And that is called the naive forecast. Now, a moving average with a window or interval of 3 will report a forecast as the average of the last 3 values in the time series. So let me demonstrate what that means. And this comes right from the textbook. So here's the 12 months worth of data, and here's our time series. This is the actual demand data. In MA1, moving average with a window of 1, moving average with an interval of 1, the naive forecast is, okay, for February, my forecast is the value in January. You just bring that down to 10. You bring the 12 down to here, 12, because I'm looking at only one interval, one window, one number. So notice 10, all these numbers here down to 16, I just move them down one time period. Okay, and so the forecast for January of the next year then is going to be 14 because that was the last value. But with a window of 3, then I look at the last 3. Well, if I average the first 3, if I average 10, and let me shade this in. If I look at, whoops, I didn't shade it. Oh, I did the pin color. Boom. Okay, let's bring this down. Let me shade this in. If I look at 10, 12, and 13 and average that, that average is going to be 11 2/3. That's going to be my forecast for the very next time period. See how that works? But then I go back and say, okay, then let me move down the next 3, 12, 13, and 16. That average is going to be 13 2/3. That's for the forecast for May. If I do March, April, May, the average of those 3 numbers is the forecast for June. And you keep moving down, moving down, moving down. So I can have a moving average with a window of 1, which is naive, window of 2, average 2, window of 3, average 3. But whatever forecast I want, if I want forecast for October with an MA3, how do I do that? I look at the last 3 values in the time series, 1, 2, 3. I average those 3 numbers. That's my forecast for October. And that's all there is to it. And that's how simple it is. Okay, so that's a moving average with a window or an interval. Okay, next is exponential smoothing. Now, and this is on page 144, and a look at example 3. Okay, exponential smoothing is a weighted moving average where the weights are exponential. Now, what I mean by weighted moving average is, notice when we average, let's say we average these three numbers, each one of them have an equal weight. Okay, if 10 plus 12 plus 13 is over 3, really each one is equally weighted. Now, if I want to weight 13 more and 10 less, well, I might take 1/2 of 10, and I might take 12, and then 2 times 13, and then average those numbers. Okay, so I could, well, or 1 of 10, 2 of 12, and 3 of 13. That'd be a weighted average. We're not going to get into weighted averages, except for exponential smoothing, because exponential smoothing is a weighted average where the most recent exponential smoothing is applied to stationary time series with a random component, where the most recent data has a much higher weight, but as you go further back in time, the weight decreases exponentially. Well, we're not going to calculate exponential weights, because exponential smoothing has a very slick way, a very clever way of doing that, a very simple way. Exponential smoothing approach uses the relationship of a forecast for time period x plus 1 is alpha, which is going to be a smoothing constant, but it can also be called a smoothing parameter, smoothing number, alpha value, whatever you call it, alpha, times the data for the time period x plus 1 minus alpha times the forecast for time period x. Okay, the relationship can be expressed with this equation. The forecast for x plus 1 is alpha times the data for x, the demand data for x, plus 1 minus alpha times the forecast for x. Now I'm using the small Greek letter alpha, it's a small a in the Greek alphabet, because it's commonly used. And so I'm going to talk about how what people commonly use. Now consider example 3, page 144. Oh, okay, let the demand, D equals demand, F equals forecast, and 1 is January, 2 is February, 3 is March. Okay. Given the values of alpha of 0.2 and the forecast for time period 2, which is February, is 142, the data for 2, which is February, is 153, using the exponential forecasting equation right here, f of 3, which is March, equals alpha, well, alpha is given to be 2, okay, that's going to be 0.2, times the data in February, which is given to be 153, plus 1 minus alpha times the actual forecast for February. Okay, and I do the arithmetic at 144.2. That's my forecast for March. And so there's the example that was given in the text. Also consider the exponential smoothing calculation in example 4, page 146, for the first quarter forecast of 175 and forecast for alpha 0.1 and 0.5. Okay, so now here's the example. Here's the time series. Here's alpha and there's a forecast. Here's alpha, there's a forecast. Now I can talk about this, but I think it might be much easier to show you how to calculate this in Excel. So now let's bring up Excel. Okay, here's Excel. Let's bring this over here. And notice right here, well, first of all, let's back up here. I did this time series here, okay? And in that time series, what I did, I pulled the time series over here, and here's my MA1, and then here's my MA3. Okay, actually the way you're going to work this in the homework is simply, let's take this, let me show you, let's take this right here, highlight it in the homework, Control C, I copy it up here, I copy it on the clipboard right here, Okay, and then I bring up Excel. Here's Excel. I open Excel up. I come over here, let's say right here, let me right here, and Control V, paste it, and there they are. Okay, and so now you can work the problem just like I did here. So MA1, type in MA1, simply will just equal the value of the data point in the time period before. And then you click that cell, the lower right hand with a solid plus, left click and drag all the way down here, and actually you can go all the way down to the forecast. And there's a forecast 14. Okay, now for MA3, let's bring this over so you can see it. There we go. For MA3 here, I want 3. Okay, so I'm coming down 1, 2, 3. So for April here, that's going to equal the average. So you have equal. Once I have equal and type in the word average, notice down here, Excel will see the word average as a function. And it says, okay, what are your numbers? Okay, I'm going to come up here and left click and drag 10, 12, and 13. And notice it goes I, the column is I, the row is 10, that's I10, colon, the I is the column, the 13 down here, or the 12 is the row, and then in parentheses, and what that will do is say, that colon says between I10 and I12, it's going to include all those values in the cells. And it's even highlighted it, it's in blue. When I press return, there's my forecast, okay? And then I can lower right-hand corner of that, left click and copy that all the way down, and there's my forecast, and that's how you do it. I can do the very same thing with Excel with exponential smoothing. So a lot of people will say, whoa, you know, this is going to be, let's zero this out. Okay, a lot of people say, oh, wow, this is going to be, okay, what happened here? Okay, somehow this went away. Okay, so here's my quarter. So let's come to here. Let's come down to exponential smoothing. And there it is. So what I want to do is take my quarters and my demand. There it is, Control C. Then I bring back my Excel and then full screen it. And right here, I'm going to bring this down here and Control V, and there's my data. Now notice in Excel, in the problem here, I said in this problem, the first quarter forecast of 175, an alpha of 0.1 and 0.5. So let's bring back Excel. So 175 is going to be the forecast for the first quarter. This is going to have an alpha of 0.1. It's already here. This is an alpha of 0.5. It's already here. So now let's do the equation. Now remember, the equation simply is, bring it up here, it's alpha times my data point. My forecast for the next time period is alpha times the data point plus 1 minus alpha times the forecast. Okay, so let's do it. Right here, this will equal alpha here times my data plus open parenthesis 1 minus alpha times close parenthesis times my forecast. And there it is. So now I'm going to click that again, come down to here, and then copy this all the way down to my forecast. And notice when I do that, my forecast down here, let's see, what is it? Let's move this out of the way, was 178. And let's move this over here. Bingo, bazinga, it's the very same number. There we go. So what I'm showing you is what I did in Excel. Let's do the same thing for 0.5. Well, you know, I could do the same thing over here, or what I could do now that it's set up here, I just say, give me a 0.5. And there it is, 184.15. Well, can I do it for 0.2? Yes. Whoops, 0.2? yes. 0.3, yes. 0.5, yes. 0.9, yes. 0.4. So once you have it set up, Excel can give you all different answers. Okay, good. Let's go on. So, but this really is a weighted moving average where the weights are exponential weights. Okay, I don't derive that. I don't show that. I'm just saying that. Good. Okay, let's go on. The next is looking at forecast accuracy measures. And we'll be looking at two, MAD and mean square error. Measuring forecast errors determines the accuracy of a forecast and consequently the forecast approach. How accurate is this approach? How accurate is our forecast? And are we using the right approach? You can use the wrong approach and it'll give you an answer, but it's not very accurate. Okay, but then even if you use the right approach, still it can give you a forecast, but how accurate is it? So there's a lot of error and biases and things you have to look at. Well, these two are two measures to address this issue. First of all, the inference is that the smaller the value of mean square error MAD, the more accurate the forecast. Okay, let the demand be D, the forecast be F, and the forecast error be D minus F. Okay, as a matter of fact, D minus F is also called the deviation. Okay, a lot of times it's called the deviation. And that's why the mean absolute deviation, well, deviation is the same as this error. Error, deviation mean the same thing. So the mean absolute deviation, where deviation is equivalent to the forecast error, is given by the MAD is the sum of the absolute value of the errors over n. So if you take the sum of the absolute values over n, that's the average. Hence, the mean is an average of the absolute values of all the deviation in the number n, where n is a number in the sum sigma, and this absolute value of d minus s is the absolute value of the difference or the deviation or the error. So now the mean square error is given by the same sum, but instead of the absolute value, it's the square of the error, or square of the deviations, or square of the differences, or square of the biases. Okay, so this D minus F has a lot of names: error, deviation, difference. Okay, and so be careful with language. People can say different words, but they mean the same thing. Okay, down here I'm actually calculating it. Here's my demand data D. Here's my exponential smoothing with a 0.1. Here's my exponential 0.1. Here's my deviation or error, same thing. Here I take the absolute value of these. So all the absolute value means is you remove the minus sign. Okay, over here is a square. You square it, and then you sum it. Take the average. You sum it and divide by 8. So now we have the MAD here. That's the mean of the absolute deviation. And here's the mean square error. The mean or the average of the squared errors. Okay. I do the same thing down here for 0.5. But let's go to Excel. And let me show you how to do it in Excel, because you'll do this in the homework. You can even use this Excel spreadsheet to actually use it and just put the numbers in and see how it's done. Okay, let's bring back Excel. So let's come down to the next, the measuring forecast error. Again, for some reason, I don't know why this happened. No worries. I will not give you something with these references in there. I will give you with the actual values. But let's do it anyway. Okay, for example 4 here, this is example 4 and example 5 both. So let's take the quarters here and the demand data, Control C. Let's bring back Excel and do it right here. I don't know what that is. We'll delete that. And let's put it in here. Control V to paste it. Yes, I have the same numbers in there. Very good. Okay. So now I'm going to use the well, I have alpha here for 0.5 whatever. So let's bring this up. I can say 0.1. Let me put 0.1 in there because I think, isn't that the first? Yeah, that's the first one. So let's put 0.1 in there. So here's my forecast. Okay, here's my deviation, and all I'm doing, okay, is equals my demand D minus my forecast F. That's all I'm doing. And copy that down and notice the numbers don't change. Here I take the absolute value. That's going to equal the function ABS. That function is the absolute value of that cell. In that cell is going to be whatever that number is, they'll take the absolute value. All that function does is remove the negative sign. Okay, press return. I come back up here and notice when I copy this down, when I let go here, those minus 7.5 and minus 15.75 just becomes positive. These others aren't changed. These just become positive. Now the squared value, and notice that caret, that upward inverted V or caret, that's really an expression in Excel which means a power. It's to the power, second power. The second power is a square. So here I'm going to equal my deviation, and then I'm going to raise it to the second power. Well, when you raise it to the second power, that's just squaring it. To the third power, you take the cube. You can raise it to any power. Return, copy this down, zip, 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 zip. There it is. Notice it didn't change. And then this will be the average. Average of all these numbers. We sum them, divide by the number in the sum. We got the average, and I can copy that over. So when I reduce this down, bring it over here, bring this over, and notice here, this is, what is this? I think this is 10 and 190. This is 0.1. I did this for 0.1. Yes, I did. See 0.1. Did I? Yep, there's 0.1. Very good. Let's enlarge this. And there it is. So you can see that's how you'll do it in the homework. That's how we did it here. So the smaller the better. Okay. So we have 10 and 190. Well, down here we have a 0.5 and we have 12 and 195. Well, 0.5 is larger. 0.1 is smaller. So 0.1 gives a little bit better forecasts than 0.5 does. Well, let's bring back Excel. We don't have to do everything. Let's come back here. Let's back up one and just make that a 0.5. And sure enough, 12.329, 12.329, not 195, 195, we got it. So again, once you have this set up in Excel, then you can go back and do all kinds of stuff. Okay, turns out to be pretty efficient. Okay, so let's go on to the next one. Okay, the next is a trend projection. So now we move away from a stationary time series to a non-stationary time series. Now we have trend. Now what do we do? Well, the trend projections apply to a non-stationary time series with a trend component. Now remember, non-stationarity applies to the time series overall nature. The trend component, a component applies to cause the variability within a time series, and that trend component is causing variability. Okay, but the non-stationary time series and trend component go together. Okay, we're talking about the very same thing, but two different approaches. Overall, from outside in to inside out. That's all we're doing. Regression approach will be used that includes an intercept term and a slope term in this relationship. The forecast equals the intercept plus the slope times time. So let x be the time period. F of x is the forecast for time period x. Let a equals the intercept and b equals the slope. This relationship can be expressed by the equation f of x equals a plus b times x. Okay, so consider this example. Consider example 8 in page 152, where y equals a forecast. A plot of the data indicates a non-stationary time series with a trend component. So I plotted the data, and there it is. See, it's going up. And actually, I regressed a line through there as a regression line. And there's the y, and there's 10.536 is the slope, 56.714 is the intercept. How do we get that? I'm getting ready to show you. And actually, Excel will do it for you automatically, or you can do it manually with Excel functions. Okay, using the regression approach, the regression line is shown in the graph. And in the graph up here, there's a regression line, and it's calculated in the table. I'm going to calculate the intercept, calculate the slope, and put it together to get my forecast. So my forecast for time period is 141. Again, I could go through this, and actually the textbook, they go through the arithmetic. Now, if you're interested, you can certainly do that. But rarely now, we have Excel, we have Minitab, we have SAS, we have R. We can do that in Python. We could we can do the Excel Basic. So you can do a lot of different things without doing arithmetic. It'll do it for you automatically. So let me show you how to do that. Let's bring Excel back. And there it is. So let's come down to trend projections. So again, okay, I still have the trend, the X and the Y here. Okay. Notice how I did this. Here's the year, but then he says I don't want to use 2000 and something. Let me just code that to an X value of 1, 2, 3, 4, 5, 7, and 8. So I'm transforming it to a code of just 1 through 8. My Y is my actual demand data. So now I have an X and a Y. I want an intercept and a slope to get my forecast. Okay, so let's do that. So here's my X and my Y right here. Again, I could have taken this, my X and my Y, Control C, and I could have brought back my Excel, and I could have just done this and Control V and just put it in there. I just did. Okay, I could have done that. But once I did that, then there's a couple of things I want to do. The first, let's just do the intercept. Okay, so now the intercept here, notice what I did here. Let me just, actually let me erase these. And let me just do them. Equals intercept. You just spell out the word, intercept. Equal, when you put an equal sign in front of intercept, Excel sees that as a function. And no, we want the known y's. Well, the y's are these. Click these. There's my known y's. Stop. Comma. Again, it's column E, row 80. Column E, row 80. Column E, row 86. It goes E80 to E86. But that colon says I want everything between those two cells. Comma. It says my known x's are going to be the x's. And there they are. In parentheses, if I return, there's my intercept. And that is the intercept. Let me do the same thing with the slope. Well, the function, conveniently enough, is slope. Okay? I'm calling them exactly what the function is. So the y is the same y as these, comma, the x is the same x as these, and there they are, in parentheses, return, and there's my slope. Now over here, I have y equals intercept plus slope times my x. Here it's going to equal, okay, it's going to equal, let's do this. This is going to equal my intercept plus my slope. Whoops, let me get it right. The intercept plus my slope times my x, my time. Okay. So let me return. Let's see, what did I not do? Oh, I don't need that. No. Okay, I don't need that. Okay, now I can just copy that down. But before I copy it down, look what I did here. If you highlight the cell and click up here in the command bar, in the formula bar, you click this, notice that it's color-coded. I'm going to have, let me click this, there we go. I have F80, that's my intercept, plus G80, which is my slope, times D80, which is my time, my coded time. So the idea here is the blue plus the red times the purple. So they even color coded for you, so you can see exactly what you're doing. Okay, and then I can copy this down, all the way down, and there's my forecast 141. And if I want these centered, I can come up here under Home, and I can center it. And there we click it, and there we go. And there's my forecast of 141. So you say, wow, that's pretty cool. Yes, it is. But you know what's really cooler? What's really nice is that, say, let's plot the data. So this is just 1 through 7. So let me plot this right here. Let me take Y, plot this, and come up here to Insert, over to the charts, and let me do this down arrow here and plot the data. Boom, there's my plot. And everyone says, wow, that's pretty nice. Well, you know what's even nicer? Oop, I didn't mean to do that. Let me bring this back. Oops. Bring this back down. Here's where I want to be. Okay, what's even nicer is you click the graph over here. Let me move this over. Click the graph. Over here on the right, you see this plus sign. Click the plus. Okay. When you click the plus, what happens is it'll come up with all these different chart elements. Here's where you can put your axis in here, axis titles. You can put grid lines. You can do all kinds of, you can edit it, okay? But one very interesting thing you can do down here at the bottom is a trend line. I can click that, and it'll give me a trend line, and there it is. Okay? And so that's exactly what I showed you in the lecture notes. Now I can double click this. Let me double click it. And over here it says linear. Well, if I double click it, it gives me more options down here. Now down here at the bottom, I can display the equation on the chart. If I click that, whoops, you can't, yeah. If it can display the equation on the chart, click that, and it'll actually say, there's my intercept and slope of the regression line, of the trend line. So let's check this out. So therefore, you can say, well, do we even have to go through this down here? Not really. But sometimes you want to, and sometimes you just plot it, get the trend line, there it is, you're done. So you can do that in the homework. So that homework problem, boom, put it in there, do that, and you're done within 60 seconds. And there's your answer. But then over here, you can open it up and start formatting it. But up here, once you click the graph over here and the add chart elements, here's where you can do all the different types of details of editing. Okay, and notice, let me reduce this a little bit. Notice my graph here, I put the axis title here, time demand. I changed the title up here. I bold this. I put all different things in here. And so I went through this add chart elements up here, and you can just play around with it and get used to it, or just Google it or go on YouTube and they'll tell you all different ways to edit this thing. Okay, so let's go on to the next one. Okay, that's regression. That's the trend line. Next is seasonality. Now remember, seasonality, trend, and seasonal indexes. Now remember, seasonality is a cyclical component, but it's a special type of cyclical component that repeats every year. Okay, seasonality in a stationary time series implies a seasonal component. A seasonal component is a cyclical component that repeats every year. A cyclical component is generally any component that repeats. Okay, consider example 9 in page 154. So what I did here's the data on example 9. I plotted the data. I plotted it here in what is called a stacked plot. And you can see here that the pattern every year is pretty much the same. It goes down, it comes up, it goes down. And so year 1 is the blue, year 2 is the orange, year 3 is the gray, and the black is the adjusted forecast. In other words, and we'll go to Excel in a minute and I'll show you how to do all this. Therefore, the average of every time period over the years represent the seasonal forecast. Okay, here's how they do it. So you have the time series here, and they have it in a table. You take the average of every year over the years for every month. In other words, those three, that 90 is the forecast for January over the years. And that's the forecast for stationary time series. And notice this is stationary. That's the forecast for January. The average for February is a forecast. So these are the forecasts. So the average of all the seasonal forecasts result in the adjusted forecast, which has a seasonality removed. That's 94. So the textbook will explain it, and I have it here as a summary. Before I get too much into the explanation, let me just take this data, go to Excel, and explain it as I do it. So let's go to Excel. Okay, and so here's example 9, page 154. So what I did here I have, again, I have the years here, January through December. Okay, so if I highlight all of this, I can go to Insert and then go back to the same chart here, Download, and go to this scatter plot. And so essentially all I'm plotting here is each one of these for January through December. Okay, and that's the actual plot that I have. Again, I formatted it to where I have time here, I have demand here, I have the legend up here, and you can see how I did it on Canvas. So I plotted it. Well, now I can see that I have the same pattern every single year. Okay, if that's true, then I have a stationary time series. Let me go ahead and delete this. I don't need it now. So I'm going to take the average. Now right here, all I'm doing here is taking the average of January for all 3 years. Okay, return, and there's my forecast. I'm copying this down for all the data, and there it is. And then here, I'm averaging all the averages. Okay, so if this is the average, this is the actual seasonal forecast for every month in this year, for year 4. Okay, for the next year, for 2010. So these represent the monthly forecasts. They're the seasonal monthly forecast. But if I average all of these, I'm averaging them and replacing them with one value, that 94 then becomes my adjusted forecast for every quarter. Well, this quite often is referred to as the seasonally adjusted forecast. And this 94 is an average. Actually, let me show you something else. Let me put it down here. Let me go average. Since I'm averaging the averages, if I average all the data, okay, from D104 to F115, I'm averaging all the years and all the months. When I do that, I get 94. So this 94 is just averaging everything. Since it's stationary, we're averaging everything to see what the stationary mean is. So this 94 represents the stationary mean, and there it is. Okay. Now we see we have variability around this. Okay. Well, what is the variability around it? Well, the variability around 94, we see that is exactly right here. And there it is. I can express that variability as an index. And the index simply is going to be my seasonal value divided by my seasonally adjusted value, or adjusted for seasonality. Okay, so let's zero these out. that's simply going to equal my seasonal value. That 90 is my seasonal forecast, so it has seasonality in it. Divided by 94, that's my adjusted value. It has seasonality taken out, so it's seasonally adjusted. It does not have seasonality. So the question is, what is the seasonality relative to not having seasonality? Well, the difference is an index, return. So my seasonal forecast is 95.7% of my seasonally adjusted value, or my stationary mean. Then I can copy that down for all of them, and there you go. I can average, and they really should average to be 1. If not, you did something wrong. So there's my indexes. So what am I going to do with these indexes? Well, I can do a lot. Okay, and one problem here, and this is not in the textbook, takes a little different path. I'm showing exactly the kind of problem you'll see in the homework. Okay, I bring down, here's my seasonal indexes. I bring down the indexes, okay, and then I say, well, you know, if I have 94 every quarter, and I mean every month, and I have 12 months, that's going to be 12 times 94. So my annual demand is going to be 1,128. That's going to be my annual demand next year. They say, well, you know, that was the annual demand for a stationary time series, but something happened. We acquired more area, more region, and now my annual demand is not 1128. It jumps up to 1,500. All of a sudden, my annual demand jumped up. Oh, okay. Now your forecasts are going to be different. What are they? Well, I can my 12 months in a year, I can divide that by 12. I'll have a monthly adjusted forecast of 125. So I'll put 125 down here for every single month as my adjusted. I'm going to seasonalize that by multiplying by the seasonal index. You know, here it's going to be my D of 125. It's going to be my seasonal index, which is my blue, times my seasonally adjusted forecast, which is in my red. And that's my seasonal forecast, and then copy that down every single time. Okay? And there you go. So you can start, so when things increase, you can multiply by the indexes and raise it. Now, again, this is going to be exactly what I asked you in the homework. You just increase this and determine exactly what the month's going to be. Now, finally, seasonality and trend. This is example 10 in the text. Let's come down to example 10. Here's example 10, seasonality and trend. Now, the way they do this, okay, well, first of all, I did this here. Continue number 2. Now consider a non-stationary time series with seasonality that exhibits a trend component and a seasonal component together. So it's no longer stationary, now it's non-stationary. So I have a trend component and I have a seasonal component. Suppose a trend now exists with a trend line of y equals 8090 plus 21.5x, where x equals 67, and represents the month January. Also suppose the seasonal index values are the same. In other words, what we're saying in here is we've done a regression and we have this intercept and slope. Our x value is 67, and now we have January. To calculate the seasonal forecast, calculate the trend line and multiply by the seasonal index for each month. I'm doing that here, but let me do that in Excel. Let me bring back Excel. So here's my A, here's my intercept A. Let me bring this back down. Here's my A, which is given to be 8090. Here's my slope, which is 21.5. That's my B. Okay. Now I want my trend, which is going to be A plus B times X, and over here's my X. Okay. And so this is simply, I'm going to do it again, equals A, whoops, oops, this way, this will equal my A plus my B times my X, and then I'm going to copy that down. And notice the numbers aren't going to change because I've already done it. Now my seasonal indexes are copied from up here. The seasonal indexes here are the same. But they don't look the same, and they're not the same. So let me make them the same. That's going to equal, oh, wait a minute, let me see if it is the same. Well, they're using these indexes. I'm going to use what they do. I'm going to do what they do, and I think that's it. That's in the text. Okay, so they're using these indexes. Okay, whatever you take the trend, multiply by the indexes, and you get your forecast. That's all you do. So now we have our trend. We have a seasonal. Here's our trend component being estimated with our intercept and slope. Here's our seasonal component being estimated with our indexes, and here is going to be our seasonal forecast. Okay, now let's put it all together. Okay, now putting it all together here, now this one, if we come back to down here, putting it all together, consider, now this is not in the textbook. I'm giving you this and showing you how to put all this together in a session. I call this a session, a forecasting session that you could likely conduct in industry. This is something, now I'm putting it all together to say, now, here's the takeaway, here's how you would do this, you're given a time series. So no one's going to say, calculate this, calculate that. They're going to say, oh, here's my time series. It's a quarterly time series, for example. I have 3 years worth of quarterly data, and there's my demand data. Okay, give me a forecast. That's what you'll get in industry. So first, remember my process. I say first plot the data, see what components you have. If it's stationary or not stationary, see what's going on. So we plot it. So down here I have a line plot, a time series line plot here, and the time series plot indicates a trend component. It's going up. I also have a stacked plot, and the stacked plot indicates a seasonal component. This is year 1, the first 4, 1, 2, 3, 4. Year 2 is the square, 1, 2, 3, 4. And notice these 4 here are greater than the first 4, and the third 4 are greater yet, and there they are. So when you have a stacked plot and you put the years on top of one another, you can see every year it's going up. You can also see the pattern within a year being the same. So what do we have? We have a trend component and we have a seasonal component. So now we have both of those. Now we have to solve it. First, let me tell you what we're going to do, then I'll show you how to do it in Excel. Down here, we block the data. And what I mean by blocking the data is I take the data here, year 1, year 2, year 3, quarter 1, 2, 3, 4, and I block it to where it's like a contingency table in statistics. The years are here and the quarters are here, and there are the numbers. Now if you look, quarter 1, year 1 is 125. Quarter 1, year 1 is 125. Let's see down there. Quarter 2, year 2, quarter 3 is 554. Year 2, quarter 3 is 554. So I just blocked them. So what you do, since you know, the reason you block it is because of seasonality. When you have seasonality, you block it to have common quarters together or common months together, common time periods together. Because now the seasonal contribution within that quarter is all together. Now the difference between the years is going to be a trend component because it keeps going up. So I take the intercept, I take the slope for quarter 1, and then I take that for the forecast for year 4. I do the same thing for quarter 2, quarter 3, quarter 4, and there's my forecast. Now if I want my indexes, seasonal indexes, I can still calculate them, but you don't do it from the forecast. You calculate them from the slope. So you take the average of the slope, which is a seasonally adjusted slope, you divide through to get your indexes. and I give the equation right there. So that's an explanation of what we're doing, but let me demonstrate this with Excel. So here's putting it all together. So first thing I want to do is actually plot this. Okay, again, you could just take the demand like this and come up here, insert, and just plot the data point, and there it is. That's exactly what I did. Then I formatted it for you. Okay, don't need that. And you can tell it's a line plot. So then I block the data. I did that right here. And when you block the data, then you say, you know, let me take these quarters here and let me plot this. Insert, data here, click, and there's my stacked plot. So once you stack it here, you can say, oh, there's year 1, year 2, year 3. Series 1 is going to be year 1. Series 2 is year 2. Series 3 is year 3. There it is. Okay. There, and so then I formatted it down here. So now I know from plotting it, I have a trend component and I have a seasonal component. So right here, okay, let me just go through each one of these. Let me just zero. Let me just take all these out and do the forecast. Let me just do everything and show you how to do this. Okay, first of all, the intercept equals the intercept of my y values, which are these three, 1, 2, 3, comma, and the x values, 1, 2, 3. Now, wait, I want these x values for every quarter. So I want the years to be the same for quarter 1, 2, 3, and 4. So now that I've just put these here, I can do F4, and notice when I do that, it puts a dollar sign in front of the columns and a dollar sign in front of the rows. The dollar sign means that it's going to be fixed. It's constant, it's frozen, it doesn't change. For example, I press return, and there's my intercept. If I do this and copy it again this way, and look at this, notice what happens here. I have the blue, but the red doesn't change. The blue changes, but the red doesn't. So I can copy this over for the quarter 3 and quarter 4, and there's the intercept for quarters 1, 2, 3, and 4 for years 1, 2, and 3. I can do the same thing with slope. The slope of my y's, comma, my x's, F4, function 4 to freeze. And if you don't have a function, then you just put a dollar sign in front of the rows and the columns. Now I don't have it in front of the D's because I want the D's to change, but I want the C here, column C, to stay fixed. And then I copy it over, and there it is. There we go. Now my forecast simply equals my intercept plus my slope times my time period of my year, which is 4. Type in 4, and now I copy this over, and there's my forecast. Now if I want my seasonal indexes, I'll take the average of my slopes. 1, 2, 3, 4. And then here I'll take my slope, which has seasonality. It's my seasonal slope, divided by my seasonally adjusted slope. F4 to freeze it, to fix it, and then copy that over, and there's my indexes. Okay, and again, this is one of the homework problems, but this is pretty much how you could do it. Now, if you plot this, and this is stationary, then you don't do the intercept and slope. All you do for the forecast is take the average of those, because it's stationary. So if it's stationary, you take the average for the forecast for quarter 1, 2, 3, 4. If there's a trend, you take the regression for quarters 1, 2, 3, 4. And that's how we're going to be doing in this course, but that gives you a lot of information on how to solve these kinds of problems. Okay, so that's all that I'm going to cover in week 2 forecasting as a foundation, as an example of how to forecast a simple time series, but also terminology will be important. Also components, definitions of components, stationarity, non-stationarity, trend, seasonality, cyclical nature of a time series. All that language and terminology will be very important. So I hope this helps. This will help you with the homework. If you have any questions, post it on Q&A, and I will visit Q&A periodically, and hopefully everyone can help each other with the answers. And if there's any answer anyone cannot get, and your colleagues cannot answer those questions, I will visit the Q&A, and I will see if there's anything I can help with as we go through. So use the Q&A link in week 2 forecasting. That's all I have. So between now and the next time I see you, stay safe and take care.